So hello everyone and welcome back. In this session we will go together through the transport of species. So with this type of simulations we have a new feature to learn today, and I'm gonna show you step by step how to construct these type of simulations. So yeah, the geometry is fairly simple. We have two domains, and these two domains are interacting with one another through an interface, and then we will see after developing the flow how to transport a passive scalar or a species, and that's very useful for concentration analysis, or let's say simulations that have chemical reactions within them. So yeah, without further ado, let's jump into the terminal and we see how to construct this simulation. Okay, this is your working directory. We open tflows, and then if we go to tests, you will find the simulation in laminar actually. And if you go to heat exchanger and we choose two domains. So as we said before, when you have multiple domains, you have as many control files as you have of domains. So, and each control file will give the input parameters to this domain. So the number of domains is specified in control 0, which is the global control file, and then control 1 represents or corresponds to domain 1, control 2 corresponds to domain 2, and so on. So in this case, before we run it, we have to make sure that we compile the code to this case. So if we go back to source, process, and then make clean make MPI, yes. So this case is quite heavy, or these types of cases, let's say 2 domains, 3 domains, it's better to run them in parallel, just to use that you can have a faster solution. And then let's refer to the case directory or the case path by case tier. In tests we said laminar, heat exchanger, and was 2 domains. So either that you take the path from the root, or that you can locate it from where you are. You can navigate through these dots. 2 dots slash backslash means that you go 1 level up, and then until you navigate through the directory to find your own case. So now we click make, and after we compile the code, we can actually in the meantime maybe go ahead and discover what's here. So control 0 is specifying 2 domains, and as we said before, when you have number 2 here, let's say, the code expects that you have control 1 and control .2 for 2 domains, and that one is just a global control file. It's just a global script that passes to the code what to expect. And you have the number of time steps, result save interval, the backup files, and the time step. And the last one here, as we said before, it's fixed. The tolerance for simple algorithm is fixed here because there is no sense behind tightening the solution or the convergence criteria on one domain and then making it a bit looser on the other domain. So it will just wait and not do anything while the other domain is computed. That's why we have the same tolerance for both domains. And then everything else is just represented or shown in the local or corresponding control file. And here the last keyword, which is interface condition. We talked about this before, that you specify the domain name, and with the domain name here you specify the boundary condition of that domain that will have an interface, or that will have interactions with the other domain. So here from the upper domain it will touch the lower domain through the bottom wall of the upper domain, if that makes sense, right? And vice versa. So the lower domain will just feel the upper domain through the top wall of this domain, right? Okay, so let's go back and see the code now has compiled already. Very good. And let me check if we still have the linked or the executables in the binary file. We have 1, 2, 3, 4. Okay, so 1 level 4, and then binaries. Okay, we have convert, divide, generate, process. We need process, we need divide, we need convert, that's for sure, because the mesh is from gmesh here. Mesh is generated from gmesh through this geometry script, and you can always modify these scripts if you like to change the geometry, or if you're validating another case, let's say, that have other dimensions, then you can go through these and then modify them. But in this case, let's say, because it's a heat exchanger and you have an interface between both domains, then they should be of the same dimension, let's say, on the interface panel. Alright, now we can use the run case actually, but let me check quickly. I have 4 processors cleaning the case, making sure that we don't have anything linked from the past, linking the binaries and removing any old control file, and linking, actually this is here linking the control 0, which is the global control file that I talked about, and you'll make a soft link or a shortcut that will say control, because in order to run the problem we need control, just a control file without any dots. And this one will refer, the code understands only this control file, but once it sees what's inside, which is passed here from this control.0, it will know that there are two domains, and then we need 2 other control files to take the parameters from. Alright, and then here you construct the mesh, if it's not constructed already, from the geometry file. I guess here in this case you have the mesh zipped already, so you can also extract the mesh, but yeah, I guess I just did it this way for another case, and it was inherited, but you can also extract the mesh directly instead of generating it, but it takes a few seconds anyways. And then here it says that the mesh successfully converted. Then actually here we should say the mesh is successfully generated, because here the mesh is generated by gmesh, and then converting the mesh through these convert scripts that come with the case already, with the case name or the domain name, and some few parameters to convert the mesh. Then running the problem finally into serial. So let's go ahead and sh, and then we say run the case into parallel mode. So we passed the word parallel as a keyword, parallel or serial in the same command, and then we put this and sign just to protect our output. As you'll see now, if you click now Control C, if you type Control C on the keyboard, it doesn't matter so much. Or it doesn't bother by your input, because it's protected in the background. The process, all of these scripts are being run in the background. It's not interrupted by your input now. So now if we go to our case, tests laminar heat exchanger and 2 domains, and maybe we can trace what's happening, output results. Then you can see that the problem is running smooth and fair. Okay, then now here is running in live, let's say. Okay, it terminated after I guess 200. It was 90 time steps only. Okay, that's a simple case. But now we just developed the flow field. Since it's finished running already, you can use this tab. And if we open ParaView, maybe instead of opening ParaView and loading the files inside, we can load them here on the same line, just so you know. You can use maybe upper domain, the last time step of the upper domain, and the last time step of the lower domain. And remember that if you run in parallel mode, you need to load these PVTU files, so parallel VTU files. ParaView understands, and they are generated by tflows. And if you have the VTU files, then this is more representing the 2D case, the serial case. If you have the VTU files, then it's more for the serial mode case. But here we have the PVTU, which is kind of a wrapper file that takes the information from these subdirectories. So sub1, sub2, sub3, sub4. Those are the domain names, subdomain names. And if you list what's inside here, for example, you will see this is sub4, right? So that's processor 4, and it carries the information and time step solutions, the boundary file, and it has the VTU file, VTU file, VTU file. So those are just VTU files, right? And the wrapper of the PVTU is a wrapper that takes the VTU files from processor 1, processor 2, processor 3 and 4, and then it wraps them together to generate or to reconstruct the domain for you in ParaView, right? That makes sense. Now we can run this command to visualize the results, or what we have now of the domain. Maybe it was a bit too early, and maybe it terminated the solution a bit too early. Huh? But let's see. First of all, the mesh is here. You can always visualize it and play with it to see. Okay, so it's a identical setup for the mesh, upper and lower. But let's say if we want to use surface to prepare for, let's say, velocity input, and here we want to use velocity also. So yeah, it's kind of interesting, because here you can see already from how the velocity profile is, the flow is fairly laminar in this case. So this is an inlet top hat profile. Then the flow develops in this direction. Then the boundary layer gets a bit thicker because it develops over time, and then towards the end of the domain is more or less a settled flow state. And then perpendicular to that, you have the inlet for domain 2, which is the lower domain. Upper domain is from this direction. So the inlet is from this direction, going with a mouse cursor here in that direction. And then perpendicular to it, you have the inlet of the lower domain from here, and it goes kind of perpendicular to each other. So yeah, up to now, there is no transport of species, it's just a flow. And now I'm going to show you how to add the transport of a passive scalar on top of this domain. So let's say we want to use domain 1. Of course, you can always visualize other parameters here. Not sure if here it will show you something like this. Okay, so you can see already, maybe if we switch this off, you can see already that the temperature is being advected, and you can kind of see something. Maybe it's a bit too early, but you can see already that it's a bit swept in that direction, the transport of the temperature between the two plates. Huh? So if you want to transport a passive scalar or a species on top of the domain, let's say you have a chemical reaction, and then you want to transport water vapor or salt or something, a concentration of something. What you do is simple, actually. You go back to the control file, and let's say we want to use control file 1. So go to .1, and that's the upper domain. So let's say I want to transport a species within domain 1, or the upper domain only. All what you need to do is you create another line here, and then you say number of scalars, and then you put, let's say, 1 for now. So you're transporting one passive scalar. Something is advected, advection and diffusion through the domain, regardless of what this thing is. But we want to advect something and transport it, that it has a passive effect on the background flow, but it's affected by the background flow. Yeah, that's it. We can close the control file for now and run the simulation again. So MPI run for, and let's say we want to run process. So let's say try out passive scalar .dat, and okay, doesn't crash. That's a good sign. Let's follow what's happening. Passive scalar.dat. Okay, that's what I wanted to show you. So let's stop here. So it's running in the background anyways. Yeah, and it's running on 4 processors. That's what we would expect. And the passive scalar, as you can see here, now you can see this guy is added to the script or the conversions history of the simulation. The first line is representing the momentum and mass conservation residuals. So you have residuals of U, V, W, pressure, mass, and temperature, and then you would have on top of them K epsilon if you have or other parameters, transport variables if you have turbulence modeling in the domain. And then, because that's for the upper domain, what follows with it is the passive scalar that we added. You can see already that T-Flow started to compute it also, and the residuals are 0. Simple reason that all the residuals are 0 because we just added the passive scalar, but we didn't really say what it is. We didn't give it any concentration, didn't give it a kick. It's just that it's sitting there, not doing anything, so that's why it's not propagated in the domain. It's just sitting there, seeded. So that's how T-Flows handles it, very simple. And then you have for the second domain the same residuals again of the first domain, but without the passive scalar because nothing is implemented there. For this simulation, the upper domain and lower domain are exchanging heat, are exchanging temperature, but the passive scalar or this entity that was just added is not passed, or it's not really exchanged between both domains. So now let's go back and kill this simulation because it's useless for now to keep exit now to keep going with it. And now to make sure, okay, so it exited, and another double check. Top doesn't give us anything running in the background, so that's a good sign. Okay, now if we go back to file again, Control-1, and then let's say we add, so the number of passive scalars that you can add to the simulation is most arbitrary, but they're limited in a default mode in T-Flows to 36, because who wants more? But if you wanted more, then you can always change the default. But let's say for this simulation we want to try 6. Again, if you want to run just the previous command, you can either do the exclamation mark, and then you say MPI, and then it will run the last command that had MPI at the beginning. Just text replacement takes the previous one. Or if it was not the previous command and then you want to look for it, then you can click or type Control R, and then it kind of searches in your history of what you're looking for. So if I start typing MPI, it shows me that you had MPI run as a suggestion, and then you can click on enter. So now a new simulation is running in the background, and passive scalar, and visualize the history a bit. So that's enough for now, and we can even kill the simulation, to be honest. So if we can do touch exit now, that's fine, because I just wanted to show you what will be printed in the output file. So now we have, instead of one passive scalar, we have 6 passive scalars, and I chose the number 6 just because then it will appear nicely on the same line with the same boundaries here, with the same borders here. And then you have the second domain, which does not have any passive scalars, obviously. So again, residuals are zeros because nothing is really being active in the domain code to code. But let's say now we want to advect the passive scalar in terms of a concentration or something that needs to propagate in the solution. So in order to that, you have to just specify a boundary condition for this passive scalar. Now I guess they're a bit too much, so let's add 2 instead of 6, and you can maybe add 2 concentrations and play around a bit to see the results. So if we go maybe to the inlet, we want to specify passive scalar 1, which will take the name C01, let's say, and then C01 will have a value of 0.01, for example. And then C02 could have a value 0.02. All right, and let's maybe give a bit of a heat flux. So let's give a heat flux. Q01 and its value is 0.005, let's say. And then we add a heat flux for the passive scalar number 2, and then we say 0.01, double the value or something. And as a variable for the bottom wall, we can say that the concentration also, so bottom wall maybe can take concentration, concentration 0.1, and we 0.01 again, and C02 will take 0.02. All right. That's good. The only thing that I wanted to hint about now is that the control file is very flexible, right? So you can add anything or any parameter, any value, any keyword in any part of the control file, except this part, because it has to identify a boundary condition. Otherwise, if you put these values in the middle of the control file, what are they, huh? So if you want to specify boundary condition, it goes exactly by the order: boundary condition name, boundary condition type, and then the values. That's it. Once we specified this, let's go. Maybe we can put an initial condition, but yeah, it shouldn't make a big difference here. But let's make an initial condition also before we go and start the simulation for these passive scalars. So let's say this one starts by 0.01 and push it to the side a bit, and C02 takes the value 0.02. That's just as an initial condition. And now let's make sure we're not running anything in the background. We're not. And we hit again our MPI run. Oops, I made a mistake. So MPI run, if we start this now, starts the process again. And if we want to tail it, we can also use the exclamation mark shortcut. Hold on this a bit, and you see we have a passive scalar 01, 02, and they started to give values. Huh? That's good. That's good. They started to give values because they are advected in the domain, and so the simulation started to do something. And obviously here also you have two maximum CFL numbers for both domains. All right, so let's see where we are at now. If we use out passive scalar like that. Okay, we finished already with I guess 90 time steps, obviously. Okay, that's good. Now we can generate the paraview files again. Okay, the same. We can see. So you can see for the lower domain, if you try to visualize the passive scalar, obviously it's only in the upper domain, so it's missing on that list, but they are here. So passive scalar 1, amazing. So it's being transported in that direction. If you visualize the velocity field, for example, it kind of makes sense. Huh? It travels with the direction of the background flow. So passive scalar 01, like that. And let's check the values here, because sometimes it can be a bit tricky. You feel like you're looking at the wrong thing. So here 0.01 to 5.9 the values are. Then passive scalar 2, you have already a bigger value for 0.02. So sorry, for C02, and you can see it goes up to 12. So it's just kind of, it looks the same, but they're different values. If you want to check here, you want to kind of clip this to the initial, the passive scalar number 1 maximum value was, I guess, 5.9. So I can kind of give you the perspective here, right? So this is C02, and C01 is like that. So you can see that the results are different. So it's just that the scaling the same thing, the same palette, but they're different numbers. So yeah, now you can see that we have already implemented or used the passive scalar option in TFlows. But the only thing that I wanted to show you next is a case that has already passive scalar into the control file, and I will tell you in a second why I want to show you this other case. So let's leave this case with the files. Maybe we need the solution, so let's not remove it now. And let's go to laminar. So now we're on that level, laminar from tests, and we navigate to the membrane. So membrane. Then you find inside also two domains of a membrane. Okay, so this case actually is more or less the same geometry, the same configuration of the previous case. The only thing that's new to you here is that the passive scalar option is passed to the code through the user mode functions. And the reason that it's done this way is that you can add all types of interactions with a code, as I mentioned earlier, through these user mode functions without touching the source code. And that's actually very good. So you can probably make some interface or interfacial forces, or you can make some exchanging dynamics between the upper domain and lower domain through the user mode functions. So obviously in this case, we definitely need to link the sources while we compile them to this specific case, because we're gonna use this guy right here. So user interface exchange. So yeah, which tells the code to exchange some properties of temperature and passive scalars between both domains. So in the previous case, we didn't have any exchange of passive scalars between domains. It was only the temperature traveling and advected between both of them, or felt between both of them at the interface. But in this case, we have an exchange not only of temperature, but we have an exchange of passive scalars as well. So in order to run this case, I would go to sources right away. I guess one level up, sources process, and we make PIS with the directory case equals tests laminar and membrane 2D. So that's the membrane 2D is the case where it has the exchange of both temperature and passive scalars as well. Directory, this tab, and open a new one. Maybe we can go to our case again. I have membrane, 2D. Okay, let's see what was in the control file. .0, which is the global. Okay, so it's more or less the same case, but we have here, you can see that we have significantly a bigger number of time steps. Yeah, so it's a case that has quite some stuff going on because of the exchange of domains at the interface between passive scalars. In order to transport a passive scalar, you can transport it without specifying anything, because it takes the keyword. So it transports the passive scalar with advection and diffusion. So it's like a transport variable, like a k epsilon, or like it has its own transport equation. But it does, if the flow does not have turbulence, then it doesn't take the diffusivity of turbulence, and then it needs a turbulence coefficient to mimic this diffusion effect. And this comes in play with this type of keyword. So if you go to documentation, sorry, I guess it's misspelled it. All keywords, if you look for exactly, so it's scalar diffusivity, or it was in the past species diffusivity. So this scalar diffusivity, you can see it's a physical property. Usually it's around 10 to -9, and here it's set the default is to 10 to -6. So as you can see, to have that effect, it's extremely slow. It takes a very long time of the scalar to be advected, and feeds the diffusion through the solution. So you can see that it's kind of a long simulation. That's why the time step is set to a very big value here. So let's check on maybe the upper domain. if we say control 1, I guess the compilation process has been done already. Ah, yeah, I see. So turbulence model is none. So it's a laminar flow case. But as I said, if you have a turbulent flow, and if you have here, for example, Cape Silent or something, then this scalar diffusivity will be taken from the turbulent diffusivity of the background flow instead of this keyword. If you go down here, actually you will see that we have one passive scalar, right? So we have one passive scalar here, advected, and it has an initial concentration, no flux, no heat flux, but initial concentration, as you can see at the inlet and the bottom wall, and maybe the second domain, anyhow, maybe that's the idea. So you can see already that the passive scalar is just initialized, but it will be overwritten by the user mod function anyways, and even if it was not initialized here, it will be felt by the second domain anyways, because they will interact with each other, right, through this interface exchange. So in this case, we're ready to go, I guess, because the compilation process has been done already. All right, if we go back and we leave this tab open, actually, because we might need it maybe to tail the solution. So now let's go ahead and run the case, run script, and then say parallel, and then we place our safety card here and simple, so it can run in the background. And you can see it's running in the background, but it's also printing us live what's happening. If it's too much or too fast for us, kind of overwhelming sometimes, you can always tail here in another tab, or because you have maybe more control with the Control C, but you can also always roll with a pen of your mouse. You can scroll up a bit, and when you scroll up, you can kind of stop freeze the simulation on your side, but while it's running in the background. So you can see what's very interesting here is that we specified the C or the passive scalar 01, and the only one in the simulation, we specified it in domain 1, but it's also transported in domain 2, right? So it's also it's working, right, in domain 1 and domain 2, while it was only specified in one domain. So that's actually what we wanted to do here, is to utilize the user mod function to have some interaction or to have some control over the simulation without modifying on the source code. And if you feel comfortable to play with the source code and implement your own models, then of course feel free to do that. But I just wanted to show you how can we utilize this functionality of T-flows. So one last thing, maybe we can actually close this. Maybe we can touch, save now, not save now, actually we need to exit the simulation. Exit now. Right, now the solution is ready for us at this time step 161. Upper domain and lower domain again, so I have to be focused with the PVTU files. If you open them, you can kind of see that you have in both domains you have the concentration. The upper domain had some concentration, and then it's affecting also the lower domain. So they are simultaneously being advected together, and they affect one another. You can see already from the simulation here. And maybe I can show you the result of a further time step that's ready with me, so we can see what happens in the end or towards the end. So I guess if we go back here, and was code T-flows tests lamina 2D. And yeah, I guess I had here 600, so that's good. Let's open another terminal with ParaView. That's upper domain, and we here have lower domain of the same time step. 612, that's good. I guess that also shows us a picture of how the passive scalar is now after a longer time. Okay, so we have a more progressed picture of the flow through both domains, and you can see that they're simultaneously impacting one another. And one last note about the user mod functions actually is that they're type of hooks, as we talked about in the previous lecture. And if we go back to, so you have this file here, or this folder, which is a user mod function that we talked about in the past. And we said that you have all of these, this list of functions, that they are kind of hooks, right? And they are empty. They are in essence empty. And once you link them, or you hook them to the current test case, or the test case in hand that you're working on, these ones are not empty. The user mod files inside test cases are not empty. They are doing a specific functionality that is suited for this case, or tailored for this case. So let's say beginning of an iteration, beginning of a time step. But to maybe give you a live exercise of how this impacts the solution, we can maybe pick something that's not hooked already. So let's say beginning of compute momentum, right? If we open this guy, so let's open user and run it, type it manually, and beginning of compute momentum, right? So let's say this is an empty file, because it's a template, and we want to use it. So if we go back to our case, I'm gonna copy this template from the back. Maybe I should have copy pasted the path, that would have been easier. User mod, and I'm gonna say beginning of compute momentum, I guess was the name. Beginning of compute momentum. Right, and I want to paste it, but not here. I want to paste it inside user mod. If you list again what you have inside user mod, at the beginning we had all of these guys, but now we added beginning of compute momentum. All right, so which should be empty because we just copy pasted it, right? But we're gonna add something just to see what would be the impact of this on our simulation, just to give you an example of what could be and how can you can utilize this tool. So let's say this is from what the name implies, that the function gets called in the main program at the beginning of compute momentum. So when you start computing the momentum equation, this function will be called. So for that, let's say print something very silly. We say about to compute momentum. About to compute momentum, right? But you don't leave it just like because you modify it on the user mod function. You need to compile again so it can kind of hook or use the new hook, right? Because now it's a bit hanging in the past. And if you go back to process, let's clean it. API, yes. And directory case, tests laminar membrane 2D. Okay. So now you're compiling and also pointing to the new function that we want to use. All right, now it has finished compiling already. We can go over original path, and yes, now actually before going back, let's go back to process a bit, and then we can list the file. And the reason that I'm doing this now, I'm trying to see the hooks or the new soft links. If the beginning, oh, okay, that's very good. We have beginning of compute momentum now, which is empty, is linking to this guy. So if you want to open it, actually, just to make sure, you can open mod and then open this guy. But before we did this, what we would have is just a template, the empty template. But now it's not really the template that's inside, it's the template pointing to this file that is in the test cases, and it's modified already. It's not empty anymore. So if you open this guy, that's indeed what you should have, or what you should see, which is the file modified by this print. So if we go back to our case again now, and let's say we want to do an MPI run again. That's actually good that we still use MPI run, because I want to show you a feature. Let's run it in 4 processors first, and then tail happening. They say backup here. In the convergence history of the solution, it keeps printing about to compute momentum, about to compute momentum, but because we're running in parallel, sometimes it's intertwined with that. So it's in an ugly way, just because we're running in parallel. But if we're running in serial, then you will have one statement before the momentum equation, and before each time it computes momentum, it will just write one statement instead of 4. So you can see already that now let's exit the solution, because it's useless to keep it running. Exit now. Okay, and let's make sure that we cleared our processes. That's good. Yeah, so this is just the only feature that that was left for this session to show you. And through this feature, you can play a lot, and you can have no ceiling basically with implementing functions and some stuff that you wanna have it interacting with the solver while it's running, or before it's running, or at the end of the time step, or at the end of the some specific algorithm. So with this user mode function, you can play with modularity as much as you want. Right, so I guess with that said, this is all what I wanted to share with you about this problem. And for the next one and the last session, we will talk about particle tracking, which is my most favorite topic in CFD, because I did my PhD there, and I'm very excited to talk to you about it. Thank you very much for watching and paying attention for this session, and see you next time. Thank you. Bye.